Ocean acidification, a change in pH by 0.1 represents a 26% increase in hydrogen ion concentration in the world's oceans. The pH scale is logarithmic, so a change of 1 in pH units is equivalent to a tenfold change in hydrogen ion concentration. Sea surface pH and carbonate saturation states vary depending on ocean depth and location. Colder and higher latitude waters are capable of absorbing more CO2. This can cause acidity to rise, lowering the pH and carbonate saturation levels in these areas. There are several other factors that influence the atmosphere-ocean CO2 exchange, and thus local ocean acidification. These include ocean currents and upwelling zones, proximity to large continental rivers, sea ice coverage, and atmospheric exchange with nitrogen and sulfur from fossil fuel burning and agriculture. Cause spatial distribution of global surface ocean pH. Panel A, the annually averaged surface ocean pH to be approximate for the year 1770. Panel B, the difference between pH in 2000 and 1770. In the global surface ocean, this diagram of the fast carbon cycle shows the movement of carbon between land, atmosphere, and oceans. Yellow numbers are natural fluxes, and red are human contributions in gigatons of carbon per year. White numbers indicate stored carbon. Duration, 3 minutes and 59 seconds, 3:59 video summarizing the impacts of ocean acidification. So, present day, 2021, atmospheric carbon dioxide, CO2, levels of around 415 ppm are around 50% higher than pre-industrial concentrations. The current elevated levels and rapid growth rates are unprecedented in the past 55 million years of the geological record. The sources of this excess CO2 are clearly established as human-driven. They include anthropogenic fossil fuel, industrial and land-use land change emissions. One source of this is fossil fuels, which are burned for energy. When burned, CO2 is released into the atmosphere as a byproduct of combustion, which is a significant contributor to the increasing levels of CO2 in the Earth's atmosphere. The ocean acts as a carbon sink for anthropogenic CO2 and takes up roughly a quarter of total anthropogenic CO2 emissions. However, the additional CO2 in the ocean results in a wholesale shift in seawater acid-base chemistry toward more acidic, lower pH conditions and lower saturation states for carbonate minerals used in many marine organism shells and skeletons. Accumulated since 1850, the ocean sink holds up to 175 plus 35 gigatons of carbon, with more than 2/3 of this amount, 120 GDC, being taken up by the global ocean since 1960. Over the historical period, the ocean sink increased in pace with the exponential anthropogenic emissions increase. From 1850 until 2022, the ocean has absorbed 26% of total anthropogenic emissions. Emissions during the period 1850 to 2021 amounted to 670 plus 65 gigatons of carbon and were partitioned among the atmosphere, 41%, ocean 26%, and land 31%. The carbon cycle describes the fluxes of carbon dioxide, CO2, between the oceans, terrestrial biosphere, lithosphere, and atmosphere. The carbon cycle involves both organic compounds such as cellulose and inorganic carbon compounds such as carbon dioxide, carbonate ion, and bicarbonate ion, together referenced as dissolved inorganic carbon, DAC. These inorganic compounds are particularly significant in ocean acidification as they include many forms of dissolved CO2 present in the Earth's oceans. When CO2 dissolves, it reacts with water to form a balance of ionic and non-ionic chemical species. Dissolved free carbon dioxide, CO, doic carbonic acid, HO3, bicarbonate, HCO3, and carbonate, CO2O3. The ratio of these species depends on factors such as seawater temperature, pressure, and salinity, as shown in a Bjerrum plot. These different forms of dissolved inorganic carbon are transferred from an ocean surface to its interior by the ocean's solubility pump. The resistance of an area of ocean to absorbing atmospheric CO2 is known as the Raval factor.